This is exercise sheet 4, question 5. It says a manufacturer of dog food wants to package the product in cylindrical metal cans, each of volume 100 centimeters cubed. Find the radius and height that the can should be in order to minimize the amount of metal used. So we're given the volume of a cylinder and we're asked to minimize the surface area, essentially. Minimize the amount of metal used, so minimize the surface area of the can. So let's draw a little picture. There's our cylinder. Here's the height. And here's the radius. So we call them R and H. Now R and H can't be anything because the volume must be 100 centimeters cubed. So once we pick one of those things, the other will be determined in order to get the right volume. So let's sort out that relationship first between R and H. So the volume of a cylinder is equal to pi R squared H. So you can find that in your maths tables. And that's equal to 100. So I can rearrange that to say that H is equal to 100 divided by pi R squared. Next, let's look at the surface area, which is the thing we're trying to minimize. The area is equal to the area of the curved surface plus the area of the two flat surfaces. So the area of a flat surface is just the area of a circle, which is pi R squared. It's twice that for the two, top and bottom. And then we add on the curved surface, which is 2 pi R H. So that's the area. That is the quantity that I'm trying to minimize. So what I'll do now is I'll substitute in that expression for H into there. So that's equal to 2 pi R squared plus 2 pi R. So I know from above that H is equal to 100 over pi R squared. So when I work that all out, I get that the surface area is 2 pi R squared plus 200 divided by R. So what I've written there is the surface area as a function of the radius. The reason I can write it purely as a function of the radius and not as radius and height is because we have the constraint on the volume. So that's why I was able to say that the height is equal to 100 over pi R squared. So we have the area as a function of radius and we want to minimize the area. So when it was y and x and we were trying to minimize y, we found a stationary point where dy dx is equal to 0. In order to minimize a as a function of r, I need to find a stationary point of a with respect to r. So that's a point where dA dr is equal to 0. So we have a is equal to all this. Let's write down dA dr. Now this is just like dy dx. Whereas here I'm getting the derivative of a with respect to r. So let's differentiate this with respect to r. We get 4 pi r. That's 1 over r is r to the power minus 1. So I get minus 200 over r squared. So that's regular differentiation, you know, except instead of x, it's r. But I've done exactly the same thing as I normally do. So for a stationary point, I let dA dr is equal to 0. So that means that 4 pi r minus 200 over r squared is equal to 0. That means that 4 pi r is equal to 200 over r squared. Which means finally r cubed is equal to 50 over pi. Or r is equal to the cubed root of 50 over pi. So that is a stationary point of the surface area with respect to the radius. And it's the only stationary point. So if it's a local maximum, then it is the global maximum. And if it's a local minimum, then it is the global minimum. So let's check. We check if it's a max or a min with the second derivative test. So I have the a, the r there. So that's the same as saying that's 4 pi r minus 200 times r to the power minus 2. So 1 over r squared is r to the minus 2. So now I differentiate again. I get d2a dr squared, the second derivative of the area with respect to the radius. So I differentiate again. I get 4 pi minus 200 times minus 2 times r to the power of minus 3. That's 4 pi plus 400 over r cubed. Now the question is that positive at the stationary point of r is equal to the cubed root of 50 over pi? And it is. Because it's pretty clear that as long as r is positive, this is going to be the sum of two positive numbers is going to be positive. So we can say that at the stationary point, at r is equal to the cubed root 50 over pi, we can say that d2a dr squared, the second derivative, is greater than 0. So a second derivative greater than 0 at a stationary point tells us that we have a local minimum. So r equal to the cubed root of 50 over pi is a local minimum of the area. And it's the only stationary point. So it's actually the global minimum. At least for positive values of r, which of course r has to be positive. So we know that the can has minimum area when r is equal to the cubed root of 50 over pi. That's equal to 2.5154 centimeters, which is what we were using. So finally we go back to our formula for the height. We know from before that h is equal to 100 over pi r squared. So I'll put in that value. And I get a value for the height of the can. 5.0308, also centimeters. So in order to minimize the surface area of a 100 centimeter cubed can, the radius should be 2.5154 centimeters and the height should be 5.0308 centimeters. And that's the can with the minimum surface area that has that volume of 100 centimeters cubed. So that's your answer. Next we do a similar question, question 7. So this one asks us to find the minimum area of cardboard needed to construct a box of volume 108 centimeters cubed with a square base and an open top. So let's draw this box. So it's got an open top. So this box has two measurements. I'll call the length of the base x, and it's a square base, so that's also x. And I'll call the height h again, just like the cylinder. So we're told, first of all, that the volume must be 108 centimeters cubed. And we're trying to minimize the total area. So let's write down the area first. The surface area of this box is equal to, well, it's the area of the bottom surface, that's x squared, plus the area of the four sides. Well, the area of one side is hx, the area of the four sides together is 4hx. So I'm going to minimize that a as a function of either h or x. But first I need to write it in terms of just one of those variables. So to do that, I'll use my constraint on the volume to get a relationship between x and h. So I'm told that the volume is equal to 108 centimeters cubed. In terms of x and h, that's x squared h. So the volume of a cuboid is just a product of the lengths of the three sides. So the volume of that box is x squared h. So what I can do with that, I can say that h is equal to 108 divided by x squared. So I've solved that for h, and I've got h in terms of x. So I can take that and I can put it back into that equation, and I get a is equal to x squared plus 4 times 108 over x squared times x is equal to x squared plus 432 over x. So there it is. I have the area of the box as a function of the base x. So now I'm going to minimize that function, a is a function of x, in order to find the minimum surface area of the box. So the first step is to find stationary points, and for that we need the first derivative. dA dx is equal to 2x minus 432 times x to the power minus 2. Because of course 1 over x is x to the power of minus 1. So that's dA dx. I could also write that if I want over x squared. So next I find my stationary points. So that those are the points where dA dx is equal to 0. So that means that 2x minus 432 over x squared is equal to 0, or 2x is equal to 432 over x squared, or x cubed is equal to 432 divided by 2. So I brought that x squared up on the left and put that 2 down on the right. So that means that x is equal to the cubed root of 216. And that works out very nicely to be 6. So my stationary point is at x is equal to 6. So hopefully now we'll find that that is a minimum. So let's find out. Second derivative test. So dA dx was equal to 2x minus 432 times x to the minus 2. So the second derivative, we differentiate that again. We get 2 minus 432 times minus 2 times x to the power minus 3. So that's equal to 2 plus 864 divided by x cubed. So it's pretty clear that this is going to be positive because we have two positive numbers. But let's just pop in our value for x to check. So the second derivative, dx squared, at x is equal to 6 is equal to 2 plus 864 divided by 6 cubed, which is equal to 2 plus 4 is equal to 6. So that is definitely greater than 0. So we have a stationary point at x is equal to 6 with a positive second derivative. So it's a local minimum. So at x equal to 6, the first derivative is 0, so it's a stationary point. The second derivative is positive, so it's a local minimum. Finally, it's the only stationary point, and it's a local minimum, so it must be the global minimum. So what actually is that area? Well, our formula for a from before is that a is equal to x squared plus 432 over x. So at x is equal to 6, the area is equal to 6 squared plus 432 divided by 6 is equal to 36 plus 72 is equal to 108. And everything was in centimeters, so that's going to be 108 centimeters squared for the area. So that is the minimum area of a cardboard box with an open top with a volume of 108 centimeters cubed. It's a coincidence that it turned out to be 108 centimeters squared, or the question was obviously constructed to come up with that coincidence, but that is the answer. So there's two examples of writing down a formula for one quantity in terms of another, and then minimizing one of those quantities by finding a stationary point and applying the second derivative test.